Ik stel voor dat we van start gaan. Welkom iedereen op deze webinar. Welcome everyone on this webinar. So there's some people, English-speaking people here, so I'll switch right into English. But all the slides are in Dutch. And so welcome on this webinar in which we'll present the results of our exploratory study of the potential of lithium and other critical raw materials in the subsurface of Flanders. My name is Johanna. I work for the Department of Environment, the team subsurface of the Flemish government, and I'm happy to give a short introduction of our study before we dive into the results in more detail. So I think most of you have heard already of the Critical Raw Materials Act. It's a European regulation that came into force 2 years ago almost by now. Amongst other things, it contains a list of 34 critical and strategic raw materials. And these materials are chosen or selected because of, on the one hand, their high economic relevance for the European Union and their high risk of supply. And some well-known examples are nickel, copper, and of course lithium, which is the focus of today mostly. There's not only this list, of course, in the regulation, there's also some measurements, some benchmarks included, basically to ensure or to establish a secure supply of these important raw materials. And there's one article that is of particular interest for geologists. That's Article 19, which states that every member state should set up an exploration program and to explore the potential of these raw materials in its own subsurface. And so the study that we will present today is part of the Flemish exploration program, which in its turn is part of the National Exploration Program of Belgium. And so what was the specific goal of this study? It was basically a continuation or starting up again of the research program that was done on mineralizations at the Flemish government in the 90s, so more or less 30 years ago. There was a lot of research going on then specifically on the polymetallic sulfides of the Brabant Massif. So this part, I don't know if you can see my highlighter. So the Paleozoic basement of Flanders subsurface. And one of the methods that was used was looking at the groundwater composition, because this is a relatively cheap, relatively easy way to make a regional survey of potential anomalies in metal content of the groundwater, which can serve as a detector of mineralized zones deeper in the subsurface. And so the studies of Sterpin are especially important for that. But back then, of course, they looked at a lot of different metals, but critical raw materials like lithium, hafnium were not really in the picture by then, so they were also not measured on these samples. So this calls for a new study. And in addition to the Brabant Massif, which was a continuation, we also have a new target now, research target, which is the Campine Basin, which is here indicated on the map in blue. And the focus there was the deep saline waters, mainly of the Carboniferous age reservoirs. For example, water that is targeted also for deep geothermal projects and which are known to contain high concentrations of lithium as well. And so basically the study was really set up in 2 different parts. One part focusing on the Brabant Massif, shallow groundwater, one part focusing on the Campine Basin, deep saline groundwater. Because of these 2 geological zones in Flanders are very different in geology. Paleozoic basement is mainly siliciclastic. The Campine Basin, the focus, at least of the samples, is more carboniferous, and of course this is also reflected in the composition of the groundwater. Also, the data sets of both study areas are very different, which calls for a different view. Nevertheless, more or less the same approach was applied, which will be highlighted more in detail later. So there were some new analyses, some new samples were collected for both study areas and analyzed. These were integrated with the historical data and put in a database which will be published on our regional database platform, DOV. This still needs to be done. Some analysis, especially historical data, are of course already present there. Some needs to be added, so a mapping needs to be done. With visualization in GIS software, spatial geostatistical analysis, the results the geochemical signature of the groundwater can be interpreted and also compared with international data, which can lead to some more future recommendations for research. All this work was carried out by a consortium of experts. So on the one hand, experts from VITO, they were responsible for the coordination of the project and the Campine Basin work. Scientists from University of Ghent did the work on the Brabant Massif, and SEK was involved for the analysis of radioisotopes on the Campine Basin samples. And as I mentioned already, the study was commissioned by us, by Department of Environment of the Flemish government. And so the program of today naturally follows the setup of the study. So first, Alemu will present the results of the Brabant Massif study area, and then Ben will go in more detail on the Campine Basin. And of course, afterwards, there's time and opportunity for questions. I also want to let you know already the full final report. The digital attachments are available on our research portal. So this includes the GIS files, the Excel extracts from the database with all the data, the groundwater data. So it is accessible by this QR code, which will come back at the end of the presentation. So don't worry. And before we really start, 3 small practical things. So this webinar is recorded, will be published on the YouTube channel of our department. The link to the recording, the presentation, and the link to the final report will be sent to all registered participants by email in the coming week, I suppose. If everyone can mute him or herself during presentation, that makes it easier for the presenters. And then lastly, if you have a question during the presentation, don't hesitate, feel free to write it in the chat, or at the end, of course, you can discuss it and ask it directly. So with that, I think we can start. So Alemu, please, the floor is yours.
Okay, thank you. Good morning, everyone. I'm Alemu from Ghent University, Geology Department. So as it is mentioned by Ioana, I'm going to present the part of the Brabant Massif. Before going to the data and the results of our part, it's important, I think, to highlight the context and also the context of this study. I mean, for the broad audience, in the Brabant Massif, based on the gravity geophysics and also based on the geological modeling, an granitic intrusive is assumed to be present at the deeper part of the Brabant Massif, which is shown actually here with the yellow color. So the thing is, these granite intrusives are geologically, they are known to be a host for different ore minerals of critical elements and different trace elements, including the lithium. So here, what in addition to that, there are different geological structures in the Brabant Massif that is mapped by the geology, which is done in 2025. So the thing is to compare spatially our results, results of the different trace element concentrations, and also to statistically to do some if there is some correlation among the trace elements basically the main one is that it's mentioned, it's lithium. Saying that, I will come to the hydrochemical data. We were able to collect about 652 analysis, which is actually on 366 boreholes. So you can understand that there were repeated analysis on wells, because these data are mainly collected. Many of them were collected from the old archives of our laboratory for applied geology and hydrogeology of Uganda. And also, like it was mentioned, we used the Sturpin's data, which is collected in 90s. And also for the major cation, we used some analysis which were done by MSc students. And on top of that, new analyses were made for the purpose of this project, which is the only database containing the lithium. Actually, lithium were not analyzed previously. Most of the elements which were analyzed were unfortunately below detection limits. So it is lithium and partly it is vanadium, which is above the detection limit, and which is used to interpret. Okay, to look roughly the boreholes which were on which analysis were made per geological formation. This is indicated in the table. When we say this, it does not mean that a certain well is only on specific geological formations, because the wells may cross different geological formations. So we were taking only the top part of the boreholes, and we tried to make an association between the analysis and the geological formations. So the formation of Oskar were the most well represented with analysis, and the second were the Madot. When we come to the results, before directly going to the results of the lithium and other critical and trace elements, it's good to see the major hydrogeochemical processes and the major water types which were happening in the Brabant Massif. We tried to use classification techniques, which is called Stepsand classification technique, which is actually appropriate for classifying groundwater types in this kind of area. The Stepsand classification technique uses 4 parameters to classify water. The first one is salinity, which is actually based on the concentration of chloride, and the total hardness, and the dominant cations and anion pairs. And on top of that, it also uses the status of cation exchange, because it's important, expected to be important hydrochemical processes in such an area. So based on this, I'm not sure whether it is clear, the maps probably. If you see the, for example, the salinity map, there is a systematic spatial relationship with salinity. In the northwest, it's more brackish, and when we go down, generally speaking, when we go down, when we go up from the northwest toward the southeast, it becomes more fresher and fresher. And also, if you see the cation exchange, it is most of the water analysis are represented by the yellow dots. This shows that the cations, the marine cations, are in excess actually the sodium. What do you mean by this? The southeastern part is it is a recharge zone, so we expect a recharged water type, a more fresh recharged water type. And the northwestern is it's the sodium chloride or more saline end member of the water. So what we understand from this classification technique is toward the northwest. In the northwest, it's more saline, which is actually in line with the neogen transgression of the seawater toward the Brabant Massif. So the seawater, the paleo seawater, is still the dominant parameter controlling the chemistry of the groundwater and also the cation exchange. So if you see the last map, you can see that the sodium chloride water types are more dominantly in the northwest, and down to the southeast, it becomes more calcium bicarbonate, and in the middle, sodium bicarbonate. The sodium bicarbonate is more dominant because the calcium, which is the recharge, dominant in the recharge part of the fresh water, is replacing the sodium, which is found in the aquifers, and taking place of it, and so that sodium becomes more dominant cation in the system. The other classification technique to support the Stephenson classification technique is the Piper diagram. As you can see here, also the dominant water types are the sodium chloride and the sodium bicarbonate, and also the recharge type water, calcium bicarbonate, which has actually distributed systematically from the northwest toward the southeast. And we tried to actually see if there is any association with the geological formations. And as you can see, a given geological formation have different water types. It is telling us that there is no association between the geological formations and the water types. That means the water chemistry is controlled by the mixing of seawater and fresh water, and cation exchange than dissolution of rocks, which was actually important for the study. The same here, as you can see, more in sodium chloride in the northwest, and towards the southeast, it becomes more recharged water type. Okay, when we come to lithium, we, as I have said you already, the new analysis were the only database for lithium. And the first thing that we have done is when is lithium called anomalous in groundwater chemistry? So we collected different, we do literature reviews, and we classify, we put this table and then compare our result with the table. As you can see, our result ranges from 0.02 milligram per liter to a maximum of 0.1 milligram. So as you compare with, for example, the deep aquifer, the geothermal aquifer, it is less. So more or less, we can say that there is no any anomaly of lithium in this part of the study. So the lithium concentration, as you can see, it's from the north, the west to the southeast. If you see, the concentration decreases, showing that the position or the position of the paleo seawater is the control, because lithium is a marine cation, so it is more concentrated relatively in the northwest, and when we come to the recharge area, it becomes less and less. We tried to do a statistical correlation between the major cations, like, for example, with sodium. There is a good correlation, a statistical correlation with sodium, because they are both marine cations, so it's expected. But also, it might be, theoretically, it might be because of dissolution, because both of these minerals may be found, for example, in feldspars and different volcanic rock minerals. So we tried to actually do, I mean, some kind of correlation, whether it is correlating with a certain geological formation or not. As you can see, along this correlation line, we see different geological formations. So there is no any specific association of with geological formation. Also, from the box plot, there is no any certain geological formation which is related with this lithium concentration. I mean, sodium and lithium concentration. So we can say that sodium and lithium are correlated, but not with certain geology. So like we said, the freshening or the seawater freshwater mixing is the more prevalent controlling factor of the system. We do also lithium because to be more sure, we do a correlation lithium with chloride. Chloride is assumed to be a conservative anion because unless there is a pollution, which is usually which is not possible in areas like the Brabant Massif, where there is a confined aquifer, which is far from pollution factors, anthropogenic factors. So we do here, there is a correlation, and then we added also the seawater mixing line. As you can see, there is excess of enrichment of lithium compared to chloride. This shows that the cation exchange, that means the replacement of lithium, like sodium, by calcium, is also another factor controlling the lithium concentration on top of the seawater and the freshwater mixing. We do also some spatial correlation with lithium and sodium. If you remember the map of lithium back, then there is a good correlation. When we come from the northwestern to the southeastern, as the concentration becomes more lesser and lesser. So there is a good correlation, both statistical and spatial correlation between the two elements. And the other thing that we have done is, because like we said, the source of lithium ores is the assumed granitic body, which is conceptually actually mapped and will be present at the deeper. So we expect that lithium concentration will increase with depths, but unfortunately there is no any correlation with depths, and also with the gravity. The gravity law, which is assumed to be the granitic intrusion. The other thing is, theoretically, it is known that lithium is associated with boron in felsic magmatism. So we tried to do a spatial correlation between lithium and boron. Unfortunately, at most of the wells where lithium were analyzed, there is no boron analysis. So we couldn't do any good, the data is not enough to do a good spatial correlation, as well as statistical correlation is not as such good. So in conclusion, as far as lithium is concerned, the concentration of lithium is highly determined by the fossil seawater and the cation exchange with calcium. But it does not mean that lithium ores are not present at the deep, because the wells that we used to analyze the lithium are shallow compared to the depths of the assumed intrusive rocks. Okay, to come to with the other trace elements and critical minerals besides the lithium, these are the different critical elements and trace elements that we could able to gather data for. As you can see from this table, the first thing that we have done is we determined a threshold value above which an anomaly is considered. And as you can see, the anomalies are found at only few wells, mostly at the upper percentiles, like the 97.7 percentiles. Above that are the anomalies of the different trace elements. So this tells us that doing statistical correlation will be meaningless because most of the concentrations are very low to low. So it's impossible. So the spatial correlation is the most meaningful association that we can do. So the way that we do the threshold is the threshold value is by using literatures and also histograms of the concentrations. As you can see, the concentrations for most of the trace elements are very right skewed, showing that or confirming that the anomaly concentrations of the different trace elements are found at only very few wells. The other one is tungsten, tin, molybdenum, tantalum, and antimony. These trace elements are assumed to be associated with intrusive mineralization, and we tried to look the spatial correlation of these elements, and we got something. They are usually concentrated in an area near Oregon over here. So there is, except the tin, there is a good, we can say, anomaly of the trace elements over this area, which we regarded as zone 1. But statistical correlation is very bad. As we have said, doing statistical correlation in this data set is meaningless because most of the concentrations are very low. The other one is molybdenum. It is known that molybdenum and beryllium and silica are associated, especially in molybdenite ore. So we tried to do both statistical and spatial correlation, and we got a good correlation, we can say. So it could be because of the associations in volcanic rocks. Could be. The other base metals, as you can see, most of the base metals are concentrated in the zone 1. There is anomaly concentration of for them, and the other part is few of the base metals have also anomaly concentrations over an area that we regarded as zone 2 over here. It could be because of the fracture systems where the hydrothermal fluids are coming and maybe depositing some minerals. It could be anything, but we got also here. But these specific base metals, for example, have different characteristics, even though they have some anomalies over these zones. For example, iron is more diffuse, while lead has also another zone in the southeastern part over here, the southwestern part. Okay, when we see most of the trace metals have anomalies over zone 1, and when we look literature, we have got that there is a depression cone, which means groundwater since the industrial period in the Brabant Massif were overexploited, especially in that specific area, in Oregon area, and drawdowns of over 100, like up to 200 meter were exploited. And then when groundwater is exploited with well, that means oxygen is letting to enter over there. So sulfide minerals which were in reducing condition will be oxidized. And in sulfide minerals, a number of trace elements are there. So these trace elements will get a chance to be oxidized and join the groundwater. So the most plausible reason for the good concentration of trace elements over zone 1 is this change of redox reaction because of this overexploitation. The others are these elements, antimony, bismuth, and arsenic. And these elements are known to be a pathfinder elements for copper, lead, and zinc. And we tried to make an association between them. There is a small association around the zone 1, but it's not a good association. So it is hard with this data set. It's hard to say there is a good association between this group of elements and the base metals. We do also statistical correlation, and the statistical correlation is not meaningful. The other one is chromium with the other precious metals, and the chromium is known in theoretically associated with the ultramafic minerals, and we tried to make an association between chromium and platinum, gold, and silver. But because the chromium anomalies are very, very small, it is not possible to do to see statistical association. I mean, sorry, spatial association between them. Barium and strontium, they are known to be related both in magmatic intrusions and also in deep brines. There is a small association in the southeast part between the two, but other than that, it's not meaningful association that we can confidently say there is. We can confidently interpret that these are meaningful associations. The other one, this group of elements are found in polymetallic sulfide minerals. So we tried to make a spatial association, and there were no meaningful association between these elements and, for example, with these elements. In conclusion, we can conclude generally that lithium concentration in this study is not, we couldn't get hydro or geochemical anomaly of lithium. And also, there is no significant statistical correlation between the different trace elements and the major cations, except lithium. This is because of the paleo marine seawater and the cation exchange. However, it's not, I mean, possible. We cannot exclusively conclude that there is no lithium or mineral beneath at the depths, because the wells, as I have said already, the wells are shallow. So it's not possible with this data set to conclude that there is no any lithium mineral. And the sulfide minerals, the different sulfide minerals that we have seen, especially in zone 1 as anomaly, most probably it could be because of the redox reaction than the dissolution of the ore minerals or the minerals in the rocks. As a recommendation, we can recommend that more lithium analysis in the zones or in the wells where other trace elements are present might be good, and also updating the geology using the different geophysical techniques in direct methods would be good, because the geology is only a conceptual map. So different things, different geological structures and the different things are not known in full confidence. The other one, and which is the most important one, is drilling a deep borehole which could reach to the intrusive and do a mineralogical and petrographic analysis will be very good. With this, I finish. Thank you so much for attending. Hello, Ioana?
Yes, yeah, I think then I give the word to Ben for the second part on the Campine Basin.
Okay, thank you, Joanna. So I'll give an overview of the analysis of the Campine Basin. The data set, first take over control, otherwise. Okay. So the data set we have for the Campine Basin is very different from what is available for the Brabant Massif. In the end, all the data we have comes from deep wells. Altogether, we had access to data, groundwater data, from 14 locations. Most of them are from the lower Carboniferous limestone. Next to that, we had good groundwater data from a deep Cretaceous well, the Merksplaats-Beerse 2 well. And then some data about the upper Carboniferous from the CBM test well drilled in Peer, and also one groundwater sample from the Namurian interval in the Turnhout well. So most of the analysis for that reason will focus on the groundwater composition of the lower Carboniferous of the limestone sequence. Altogether, we had 119 groundwater samples. From these wells, but the quality of these data is highly variable. As it are samples from deep wells, for example, there is a difference in where the samples have been taken and when the samples have been taken. Most of the samples were taken during or very shortly after the well had been drilled. In some cases, it's clear that there was a cleanup of the well before. In some cases, that's less clear, so that's already a point of uncertainty about the data quality. Some of the data are from production tests with indication of the moment within this production test, so that definitely gives a better feeling on how clean the water could have been. And then some of the data mainly data from the Peer well and data from the Vito geothermal project, but also new samples taken at Beerse. They came from moments that there was production, assuming that we really have an idea about the actual reservoir composition. As I said, the other element is where were the samples taken. Also, that's different. In most cases, there are surface samples. They can have been taken in the case of geothermal projects, for example, just before or after the heat exchanger. That's already a difference. Some of the samples are downhole samples, which at least to my feeling are more reliable, because in that case you can assume that samples were taken under actual reservoir conditions with limited or no degassing and risk of precipitation while taking the sample or by the ascending of the fluid towards the surface. Now, this uncertainty about sampling procedure also is reflected in a variable quality of the analytical data that is available. First of all, there is a difference in the way the samples have been taken and conserved or not. And also different analysis procedures have been used, so that definitely can influence the actual data you have. But that's all documented in the database, so you can do a screening for yourself to see, okay, what samples are reliable to my field and what samples are not. Looking then at the data from these 119 samples, only 64, so about 50%, have a full set of major and minor elements needed to calculate an electron balance. And about half of the samples have an electron balance within 10%. So these were taken as the main samples for the further analysis. Then looking at groundwater quality, the picture is quite different from the Brabant Massif. Here you don't see much spreading. Looking at the Piper diagram, so all samples are of the sodium chloride type, with sodium and potassium being the dominant cations. There is some correlation with the lithology, especially with respect to calcium and magnesium, where we see that they are slightly more abundant, or the relative abundance at least is higher in the carbonate reservoirs versus the siliciclastic samples from Peer and this one Namurian sample from Turnhout, but that's also not a surprise, being the difference a carbonate reservoir versus siliciclastic reservoir. Looking at the Stuyvesant classification, we see that except for the Cretaceous sample, which is a brackish sodium chloride type of fluid, all others are hypersaline or very saline to hypersaline sodium chloride brines, with a medium to high alkalinity. Also striking from the samples is that all samples except for the Cretaceous show a deficit in sodium, potassium, and magnesium, pointing towards cation exchange or other chemical or water mineral interactions that resulted in depletion of these cations in the formation water. As will be shown later on, this comes with an increase, especially in the calcium content of the formation water, which again is not really surprising looking at the carbonate matrix of most of the samples. Then another aspect is what about skewing of the data with respect to mineral precipitation before taking the sample. When we look at the calcium saturation index, we see that most of the samples have a calcium saturation which is close to zero, which again for a carbonate reservoir does not come as a surprise. But there is no indication that at least for the deeper samples, the lower carboniferous samples, there is a really oversaturation of calcium. So although calcite precipitation during sampling or just before sampling cannot be totally excluded, at least it is interpreted as being minor at the best. The only exception is the Cretaceous sample, which shows some level of oversaturation. So in that case, skewing due to calcite precipitation, and skewing mainly with respect to the bicarbonate content or the carbonate content, and the calcium content cannot be fully excluded. Then to have an idea about the origin of the fluids, the first thing we did is we had a look at the main water chemistry, so from major and minor elements, starting with an evaluation of the trends we see in the conservative elements. So elements for which you can assume that there is little interaction or no interaction between the formation fluid and the rock matrix. And the first plot to be made then is a sodium chloride plot, because it can give you an idea about the contribution of halide, dissolution of halide to the fluid, but also gives an idea about possible mixing of seawater with river water, or evaporation or drying, dehydration of seawater. Now, what we see in the sample is that the Merckx plus Beerse 2 sample, so the Cretaceous sample, it plots on the mixing line between seawater and river water with a ratio of river over seawater of about 60 to 40. The lower Carboniferous samples, they all point to an evolved seawater composition with a salt content up to 5 to 5.5 times the seawater concentration. They also plot along the evolution line that you can expect for dehydration or evaporation of seawater. So that's a very likely source for the brine that we encounter in this deep limestone reservoir. You also see that there is deviation from this line. I come back to that later. So it's clear that, especially with respect to sodium, there are other processes that are affecting the water composition. And on the pair sample, that's the only exception. It really plots nicely on a line that is expected for halide dissolution or the mixing of a halide-derived brine with river water. This might point to a contribution from a hypersaline Zechstein fluid. However, that hypothesis could not be further evaluated due to the limited data set, both with respect to the available trace elements in these pair samples, but also the lack of additional wells to verify that hypothesis, especially then wells in the eastern part of the Campine Basin. As I said, sodium, the sodium chloride trend, especially for these lower Carboniferous limestone samples, they show quite some deviation, especially the sodium content from the theoretical evaporation or dehydration line for seawater. So further evaluation of possible sources then can be done by looking at other conservative elements, and then the best to start with is boron, and to see how it compares with respect to chloride. This chloride bromium, chloride bromium ratio has been used and also shown to work in the past to make a distinction between primary seawater derived brines, which typically have chloride bromium contents below 650, and secondary brines, so brines where there is a contribution from leaching of chloride-rich salts, which typically have ratios above, and in some cases well above 650. When we look at the samples, again, the sample from Merckxplas and from the Merckxplas BRC2, the Cretaceous sample, nicely plots on the trend that you would expect from river water, seawater mixing. Again, at about the same 60-40 ratio of what was derived from the chloride sodium relationship. The lower Carboniferous samples, on the other hand, they all have values that are above this 650, suggesting that the actual source of or the actual brine is a mixture of both a slightly evolved, slightly dehydrated seawater and a chloride enriched deeper basement brine or secondary brine. That with respect to the conservative elements, next to that, most of the other major and minor elements are to some extent affected by the interaction of the fluid with the rock matrix, and deficits or excesses in some of these cations then can be used to get an idea about possible processes that may have further changed the groundwater composition. So looking at these other non-conservative cations, the first thing that's striking is the fact that there is a quite strong deficit in sodium, potassium, and magnesium in these lower Carboniferous samples. A similar deficit would be expected from when you are mixing a seawater-derived brine with a deeper basement brine. How these trends, theoretical trends, for two different different ratios of two different stages of seawater dehydration are shown here in the graph to the left by the green dotted curves or dashed curves. As you see, okay, it might this mixing might explain some of the deficit we see in the samples. However, the deficit is way stronger, suggesting that other processes are affecting the sodium, potassium, and magnesium content in this deep limestone groundwaters. Looking at the Cretaceous again, it's really on the or very close to the river water seawater mixing line, with some depletion that can be explained by cation exchange, especially a reduction of the sodium content in this case, due to expulsion of sodium by calcium in this carbonate reservoir. As you can see in the graph on the right, this deficit is to some extent compensated by an excess of calcium in these lower Carboniferous groundwaters, which already indicates that exchange with the carbonate, with the calcite matrix, is to some extent explaining the water composition. Also, cation exchange of sodium and potassium due to calcium are likely processes for this the depletion seen in the first group of cations. Then when we only look at potassium content, we again see more or less the same things. So the mixing of river water, seawater, with some carbonate exchange for the Cretaceous sample. Here again, the sample from Peer is indicative for this halide dissolution with some, but with quite limited probably cation exchange, and then the lower Carboniferous sample. It's obvious that all the lower Carboniferous samples have an excess of potassium, which can be explained, or to my feeling is explained by contribution of or an enrichment, a slight enrichment of the brine in potassium due to interaction with calcium-rich minerals. Then looking at the trace elements, we used a different approach than what has been done for the Brabant Massif to identify whether a sample is enriched in a certain trace element or not. What we did is we used a seawater corrected concentration to see. We calculate the seawater corrected concentration, and in case a sample had a trace element content that is at least 10 times as high as what could be expected in the seawater, then could be affected from this seawater corrected concentration. But then we say the sample is enriched in that trace element. In case we use that approach, we see and we look at the data set. We see that a number of elements are enriched in at least 10 of the samples. They are listed here. The strongest enrichment factors we see for barium and lithium, which are enriched by a factor of 100 to 1000, so quite strong enrichment with respect to an evolved seawater. Also, aluminum is in some cases strongly enriched. However, looking at a very low solubility of the element in deep groundwaters, it is more likely that these high enrichment factors that are seen in some of the samples are not really reflecting groundwater composition, but more likely due to contamination by clay minerals. Also, there is no clear correlation with of this aluminum enrichment with other elements. It's also quite erratic within certain data sets, so that's why we say it's likely due to contamination and no further evaluation of this component. Although it could be very interesting with respect to understanding mineral fluid interactions in case we would have had good aluminum data. So the first element to look into is lithium. There we see concentrations in the data set that range from about 2 to about 130 milligrams per liter. And we also see that all the samples from the lower Carboniferous are enriched with enrichment factors of about 100. We also see that there is a a positive correlation, especially with potassium, to a lesser extent with calcium, but that can be due to the fact that the most enriched samples come from this carbonate reservoir, low carboniferous carbonate reservoir. But there is a very good correlation also with potassium, which suggests that there is at least some similarity in the processes that led to the enrichment of lithium in these lower carboniferous samples. The trends that we see are in line with cation exchange. So lithium is the most easily expelled from the monovalent cations from clay minerals, and then the fact that especially in this limestone reservoir, you have a very strong presence of high concentration of calcium that can have resulted in an expulsion of additional lithium in these deep limestone formations. So the most likely causes for the enrichment are cation exchange, but also alteration of muscovite or elitization, which then also would result in especially the last process here, in an increase of the potassium content, can have contributed to the enrichment. The other very strongly enriched element is barium. There we see enrichment in basically all samples from both the upper carboniferous and lower carboniferous. For the upper carboniferous, we see a positive correlation with the sulfate and the bicarbonate content. For the under carboniferous, the correlation is mainly with potassium. So in this case, the controlling processes are believed to be for the upper carboniferous interaction with barite-rich minerals. It can be barite, it can be barium-rich carbonates that are present in these formations. For the lower carboniferous, most likely enrichment here is by expulsion, cation exchange, or other leaching processes from clays, or alteration of mica and/or feldspars. Third element that is enriched in all lower carboniferous samples, though to a lesser extent than lithium and barium, is strontium. That's not to be a surprise because of the replacement of calcium by strontium, some carbonate minerals. So here the interaction with the carbonate matrix is the most likely cause of the enrichment that we see in the lower carboniferous. For other trace elements that have been enriched, trends are much less clear. What we see in general is that most of these elements show the strongest enrichment in the samples that come from the Beerse area or from the Loonhout area. There is, in some cases, significant inter-element correlation, which at least suggests that they are influenced by similar processes. And for some of them, we see a weak correlation also with the sulfate content, which makes me to oh yeah, somewhere. A microphone that went on, which could point to a contribution or an enrichment of these elements in some of the samples due to alteration, oxidation of sulfide. Of sulfide minerals known to be present, especially then in the more organic rich parts of both the limestone and the overlying formations. So with respect to lithium and possible enrichment processes, the conclusion is that the enrichment is mainly due the combined effect of first of all a dehydration or further evolution of a primary seawater derived brine in combination with mixing of a deeper basement brine that can have added additional lithium to the formation waters in the lower Carboniferous, in combination also with cation exchange that led to a further enrichment within this limestone reservoir. We also see that lithium concentration increases with depth and also increases then with formation water temperature, which is in line with an intensification of these processes with increasing temperature. Okay. What we also see is that there is a clear correlation between the lithium content and the magnesium-lithium ratio, where we see a decline of the magnesium-lithium ratio with depth. The samples from the phytogeothermal site having values below 10, which for lithium extraction from the brine is positive, because the lower this value, and especially values below 10, have result in an easier extraction of lithium with less competition, especially with respect to sorbents that are used to extract the lithium from the brine. So conclusions for the Campine Basin. There we can state that with respect to the composition of the groundwater, all groundwater samples are from the sodium chloride brine, which where we see that the concentrations of sodium chloride, but also of most of the other major and minor elements, increases systematically with depth. With respect to the origin of the brine, we can conclude that it's a modified seawater brine, probably a mixture of a slightly evolved seawater derived brine with a deeper hypersaline basement brine. That's at least for the lower Carboniferous. For the pear sample, some influence of a halide-derived Zechstein type brine seems likely, but as I said, could not be verified due to the limited data set. It's also clear from the water chemistry that it's consistent with an old brine that has been in contact with the carbonate reservoir for a long period of time, and that is quite closed system. Then, with respect to critical raw materials, the most interesting elements for the evaluation are lithium and strontium, which are both enriched in the lower Carboniferous groundwater samples, where the lithium enrichment is likely coupled at interaction of the brine with phyllosilicates related to dissolution or remineralization processes, in combination definitely also with cation exchange. For strontium, it's what we see is what can be expected from interaction of a brine with the carbonate matrix, resulting then in a slight enrichment of strontium in these formation waters. Then another element, another aspect from the fluid that we examined is the presence of radioisotopes and what it could mean with respect to the formation of naturally occurring radioactive materials in case you start extracting other metals from this brine, or in case you are producing geothermal energy or another process or another application in the deep subsurface. Next to that, we also want to see to what extent then especially uranium isotopes can be used to get an idea about the origin of the fluid. That's due to the fact that the uranium isotopes are influenced by the source being uranium, naturally occurring uranium-235 or thorium derived. However, looking at uranium concentrations in the samples, in fresh samples that have been taken at Loonhout and in Beerse, we see that the concentrations are very low. So these are becquerel per liter. So to translate that, it's below or well below the ppb range. That's with respect to the second objective a pity, because it didn't allow us to do an evaluation of possible sources of the fluid. But on the other hand, not really a surprise looking at the reducing conditions of the in the lower carboniferous limestone reservoir, which results in a very low solubility of uranium. Then looking at the second objective, what with respect to the processing of that type of brines, there it's mainly the radium content that is of interest, and then the most abundant radioisotope in the formation waters is radium-226, with values that range from about 60-65 to about 150 becquerel per liter. So it are quite elevated levels, which in all cases are above the exemption level of 3.6 becquerel per liter that's stated in the relevant regulation. Which means that in case you want to process or want to transport that this fluid, you also need a permit or an approval by FANC. The possible sources of radium, there are two. For the 226, it's uranium that's present in the formation matrix. For radium-228, which is also present in the samples, though at lower activity levels, the source is thorium. Possible sources here are both the organic rich deposits that form the caprock of the lower carboniferous reservoir, but also organic rich carbonate layers within the limestone sequence are possible sources of for this radium. Radium itself is not the most problematic when processing the samples due to its high solubility under most conditions, both at surface and in the reservoir. However, when radium decays, you have the formation of radon gas, which can pose risks, especially when storing the sample. And other daughter elements are polonium and lead-210, which are solid particles, which can clog the installation, which can clog filters, and then can become naturally occurring radioactive materials that have to be disposed of. Okay, that brings me to the conclusions and recommendations that we made after the study. So altogether, we had identified 3 areas where we see enrichment of certain trace elements. So one is the Campine Basin, especially the lower Carboniferous limestone reservoir in the basin. And then we have 2 areas where we see enrichment of certain trace elements in the Brabant Massif. The first one is in this Oost-Roosbeke, Waregem-Harelbeke region. The other one is further to the east near Oudenaarde, Oudenaarde-Gerardsbergen. So with respect to the Brabant Massif, this first zone, the Oost-Roosbeke, Waregem-Deerlijk zone, there we see enrichment in a large group of trace elements. In the second zone, it's mainly the base metal, or some of the base metals that seems to be or that are enriched. Here, the recommendations, which are a repetition of what Alemu already said, is to do further evaluation to see what are the whether there are other indications for example, relationships with lithium by doing additional groundwater analysis. But most important will be a refinement of the local geology to get a better understanding of what could be the enrichment processes and to what extent the rock and the geology, the rocks and geology can contribute to the enrichments that we see, especially in this zone 1. Where we definitely also have this overprint from the groundwater depletion. With respect to the Campine Basin, focus is mainly on strontium and lithium, with recommendations to further investigate the possible sources of lithium. So I think from the analysis we did, we have an idea about the processes that control the lithium content. However, it's unclear, for example, whether the lithium, the real source of lithium, comes from the caprock, from carbonated, from clay-rich intervals within the lower Carboniferous, or possibly also from the underlying formations from the Devonian and mica present in these Devonian samples. So to further explore that, mineralogical and geochemical evaluation of the lower Carboniferous limestone and the over and underlying formations are recommended. Also then looking at the possible influence of organic matter in further enrichment of lithium, which cannot be fully excluded from the data set. Further on, we made a recommendation to extend the data set for the Campine Basin with high quality data by, for example, taking up recommendations with respect to groundwater sampling in new geothermal wells or in other deep wells that are drilled in the Campine Basin. For that, we also recommend to to make this this obligation in combination with a minimal parameter list, especially to include elements in the analysis that are typically left out because of limited economic value, but very interesting with respect to the origin of the fluid. And then I'm mainly thinking about bromium, boron, jodium, and fluoride, even in combination with isotopes of some of these elements. And then finally, also to compile a database not just of groundwater chemistry, but also from mineralogy and geochemical data about the rock matrix itself, because that would be interesting for further geochemical modeling. Okay, Johanna.
Yeah, thank you very much, Ben. Also, thank you, Alemu, for the interesting presentation. We talked a bit more than planned, but we still have 10 minutes for questions, so I propose we dive right into it. There's already one question in the chat for you, Ben, for the conservative ion graphs in slides 40, 41, the axes are negative. And yeah, the question is, why are they negative? So maybe we can go back to slide 40 as an example.
Yeah, the axis, it's I plotted in negative because of it's milliliter equivalent per liter indeed. What is shown for chloride, not for the excess. So the excess concentrations for sodium. Well, first, maybe better to go back to it. Still sharing? No. Yeah.
Yes, we see.
Yeah. Okay. So the excess values, so the sodium, calcium, magnesium, and sodium, potassium, magnesium, and calcium values that are in the end the calculated excess or deficit values. With respect to what you would expect from a similarly evolved seawater brine. So this can be both positive and negative, depending on whether there is an excess or a deficit of these cations. For chloride, I plotted them negative because of the negative charge of chloride.
I hope this answers the question. Otherwise, feel free to take the word. Are there any other questions in the meantime? You can just unmute yourself and ask your question directly. Everyone's invited. No one? Well, in any case, okay, Wouter,
maybe,
go ahead.
Small question. Hi, I'm Wouter Geilen. A small question for Ben. Was it possible, based on the limited data set you have on the drill holes, to investigate any relationship with deeper faults in the Campine Basin?
No, the data set is indeed too limited to have a look at that. Yeah.
So you don't have a real idea whether you have any contribution from a expulsion of deeper fluids from the Devonian or from the deeper basement to these low carboniferous aquifers.
No, the only indication we have is that there is a contribution from a more evolved brine, but what its source could be and whether it's fault related, that's not cannot be said. No.
And then another question maybe. I saw in your recommendations you mentioned a number of things what we could do to improve our knowledge on the subsurface. If you look at the drill hole database at the DOV database, then you often see you see that there are actually quite a lot of drill holes that have reached or penetrated the lower Paleozoic basement, for example, the Brabant Massif. However, the descriptions that are often given by these, of course, commercial drillings are very poor. They often say just rock or green rock or red rock or something. Is there any opportunity or possibility to demand for more from these drilling descriptions? Because that would, of course, increase our knowledge much more if you have trained drillers or trained drilling crew that can better describe the observations and the observed rocks.
Yeah, I can only agree to that, and it really then depends on the crew that's in the field, how good the description is. So I think that's maybe something that could be taken also up by universities, or to have better training, so that that people can do proper descriptions in the field. That definitely would help. Next to logging, which traditionally now is, especially in the deeper wells, is being done.
Okay, thank you.
Also, a question from Bailey in the chat, asking if at the Lago well in Brede, they're also been looking into this. Maybe I can answer as well.
Yeah, you can.
Because yeah, the thing is with deep wells in the Brabant Massif, they are often dry, and so to obtain a water sample that is representative of the water in the Brabant Massif is very difficult. So yeah, they have logged, made the loggings, but they have no water samples. It's meant to be to function as a closed system. So I don't know if you want to add anything to that, Ben.
Yeah, no, that's indeed so. So no water sampling. It was not. It's not foreseen neither to produce fluid, or not from the rock itself. It's
Okay, then I think all questions that are all burning, urgent questions have been answered. I think we can conclude right on time. If in the future there's any more questions, of course, you're welcome to read the final report, to browse in the data sets and the GIS files yourself, or contact one of us in case you have more questions. I want to thank again Alemu, Ben, for the presentation today, but of course all the other team members that contributed to the research since last year till now, from you again, from Vito, from SEK. And thank you to the audience as well, of course, for your presence, for the questions, and for your interest. And so hope to see you soon on another occasion. Have a nice day.
thank you.
Thank you.
Thank you.
Have a nice
Bye.
day.